Uh, okay, so let's resume. At this point, I feel like the adversary. I'm the guy standing between you and the whatever, right? So you know, it is what it is. Well, we were having a discussion earlier about information theoretic security. Like, you know, information theoretic security is if your one way of thinking about it is if your prior distribution is the same as your posterior distribution, then you learn nothing, right? And I feel like I'm converging towards that. I'm converging towards information theoretic security. Your knowledge of what I'm saying, the prior and posterior start beginning to converge. So, but anyway, you know, so okay, let's start operating potentially at a slightly higher level, which is always very tempting, right? The proofs don't matter, the big picture, right? So let's, for this last hour, try to focus a little bit on the big picture. I'm sorry? Humanities lecture. Okay, fine. But you know, we are human. That's what we do. So we'll go with that. And I do promise I'll try to finish on the dot or close to 4:30. I'll try not to succumb to the temptation to show you how clever I am and how hard I've worked and all the various stuff I've done, right? But I will hang around afterwards. I'm happy to chat about things that people would like to talk about. So there's always that. Several people have also asked if the slides will be available. The current versions aren't very polished. If you send me an email, I'm happy to email the slides to you. Also, some version of the talk may be available on video and so on. So there'll be all of that. Okay. All right. So before the break, we talked about myopic channels. We talked about Alice transmitting something, James getting to see a noisy version of that, and then adding some noise, and then Bob trying to decode, right? And that was, we looked at it for the specific case of random binary symmetric channel noise towards James, and then James then adversarially flipping some bits, right? So BSE Q here, and adversarially PN bit flip here. But you could imagine replacing this channel with an arbitrary discrete memoryless channel, W of Z given X. You could imagine this being an arbitrary state vector S, and then you could imagine this being an arbitrary really varying channel, W of Y given X comma S, right? All of this. And then what can you hope to say over here? So we can actually very satisfyingly or reasonably satisfyingly, we can say something which is reasonable, which is what we would hope to be able to do. We'll have to parse this at several levels, but first of all, we can prove that you can get a certain rate, you can get to the capacity of a certain channel. We'll worry about this expression later, but you can get to the capacity of a certain channel as long as you're sufficiently myopic. So this version corresponds to the sufficient myopicity. Why? Well, for example, for the bit flip case, this corresponds to the capacity of this channel, of this BSC here, is 1 minus h of q, right? That's the capacity of a binary symmetric channel with crossover probability q. As long as this mutual information is less than the smallest mutual information that can be imposed by the adversary, so this I of x comma y. Now notice x to y is not a discrete memoryless channel. The adversary can behave, you know, in a non-memoryless manner, but look at the worst memoryless adversary, look at the worst random noise adversary, that if the adversary chose to behave like a memoryless channel, so then what is the smallest mutual information he can impose on the right hand side? So as long as this condition is satisfied, that is, this DMC is always has a smaller capacity than the worst DMC that the adversary can impose, that's what we would call our sufficiently myopic condition. Then in this case, you can get the capacity of that corresponding smallest mutual information. You can actually get to that capacity. Okay. I'm sorry, not even with the there's no penalty term, because we're not aiming for secrecy. We will in a later statement aim for secrecy as well. That penalty term only comes around for secrecy, but you can indeed get through to this. So if the statement stopped over here, then that would be really, you know, what one would naturally aim for, right? That would be what one would aim for. Unfortunately, and this is why it's not fully satisfying, we don't really quite have that. We need to add another condition which further restricts the state space. This I actually view as basically being a technical condition. and we are working hard to try to remove it. We are not quite there yet. We have some ideas on how to do it, which I may or may not try to outline depending on, again, big picture and mental stamina and all of that. But near the end of today's talk, we may begin to see how to remove these conditions. But basically, I view this as something that we need to make our proof go through, but may not be fundamental. Okay, so something to keep in mind. And yeah, okay, I'm not going to try to describe that extra thing in more detail, again, because we're talking big picture, right? But yeah, so let's just let's just also reiterate some points. So you can't hope for a rate higher than the mutual information of the worst DMC, right? Because James can always behave like a DMC. You can't hope for anything greater than that. So you can't hope for anything more than that, but it's interesting that you can achieve that. This next thing is James should be worse off compared to Bob. So if we want to try to replicate our earlier proof, which is that there's a exponential, at least 2 to the epsilon n possible code words that Alice could have transmitted, and then James is confused about that, and you want to try to do something like that. So we'd better hope that the mutual information from Alice to James is smaller than the worst mutual information that he can impose from Alice to Bob, right? Otherwise, at least our earlier proof technique has no chance of succeeding, right? So that's why we need that second condition. From a purely achievability perspective, it's not obviously fundamental from a converse perspective, okay? All right, so yeah, now this last condition is, okay, well, let me just say a little bit. The reason for this weird summation on the left-hand side and so on, it really just comes down to what I believe to be a loose bound relating to list decoding plus reverse list decoding. If you want them to be simultaneously achievable, then we need some technical conditions, and that's what comes around over here. I'm not going. Yes, sure. So there's some question about this. Yes, there's also a question.
When you say the memoryless like channel,
yes,
the binary relation channel, that is clear. But general channel, there is some type.
Yes. So that's a good question. So there's a couple of questions. Let me repeat those for the audience, and let's just, since we're operating at a high level, let's make sure at least a high level is clear. So answering the second question first, what does the DMC like behavior mean for general AVC is the question. So generally speaking, usually in AVCs we say that the S should be within some S intersection. I think we called it gamma, and usually this gamma is some sort of convex collection of type classes of S. So let's give some examples corresponding to this of S. So for example, if for a erasure or a bit flip channel, it could be it could be that we are interested in type classes corresponding to the Hamming weight of S being within a certain range. Let's say n times n times alpha to beta, something like this, right? So this is a convex collection of type classes, right? In other cases, it could be more complicated. We could have not just upper and lower bounds. You could have some linear combinations, like maybe S is a ternary vector, so maybe S is in the set 0, 1, 2 to the n, and now you have combinations like the number of S1s plus 2 times the number of S2s is less than 3 times n, and the number of S3s plus plus 5 times the number of S1s is less than 4 times n, some convex combination like this, and again that will be a convex combination. So typically we often restrict ourselves to linear sets of type classes like this. Okay. Now within these things, you can now say, okay, so given these restrictions on S, you can ask yourself, given my channel W of y given x comma S, if I restrict myself to a type class from this set, what is the worst W of y given x that I can impose for a fixed type class, and then minimize the mutual information over the worst such type class. So that's usually what's done over there. Yeah. So hopefully that helps answer that question. The other question was just to try to understand this, and again, it's hard to understand in general, but let's look at one or maybe two cases to get some intuition for this. So for a bit flip adversary, let's look at what these conditions collapse to. So on the right hand side, for a bit flip adversary, what is h of x given z? So the adversary sees z. So on a per single bit basis, how much uncertainty does he have about x? He has, I was almost going to, so usually I'm used to projecting on a whiteboard, and I was almost going to write on this, so luckily I remembered not to. But the right hand side would be less than or equal to hq, right? Because the adversary is seeing z, so his uncertainty about x is like hq, right? Over here, now, let's look at this term first. So if Bob is seeing y and s, so he sees what he sees, plus he knows whether the adversary flipped a bit or not, so he has no uncertainty about x, right? So this is 0, this collapses. This is how much uncertainty is there about the output given the input. Well, this comes down to whether James flips a bit or not, so this is like HP if the adversary behaves memorylessly, right? So this condition basically becomes HP is less than HQ, which is the same, at least if P is less than Q, right? So it collapses to the previous condition over here, okay? So, okay, so at least in this case, it doesn't seem to add anything to the problem, right? It actually is the same as what we already know how to prove. Unfortunately, in even things like the erasure case, so if this channel is an erasure, this is an erasure, this is a random erasure, this is an adversarial erasure, you can try to do this calculation again, and it'll turn out to be weaker. It'll turn out to be something like P plus HP is less than HQ, and whereas if we prove the capacity thing directly, we can actually still prove something like this. So this is a smaller region. This turns out to be a smaller region than this region. So if we impose this extra condition, then for an erasure myopic channel, we can prove a weaker result than if we did the calculations more directly, like digging our hands into the guts of the proof. Okay?
Why you think this can't be just thrown out?
I'm sorry?
Why you think this condition may be discardable?
Yeah, that's well, that's an example of where this condition is discardable. There are more fundamental, like once you start looking at the geometry of the problem, there's something happening where you have to relax the notion of list decoding appropriately, something we're now calling myopic list decoding, and under this suitable relaxation, we're able to expand the region where things are possible, okay? But ongoing work. So, all right. Any other questions to do with this before? Okay. So without at all going into the proofs, the proof techniques are quite similar. So again, there's a oracle given set, there's a sufficiently large confusion set, there's an oracle given set, he reveals the type class, so instead of the Hamming distance, he reveals the type class in the oracle given set. Then you again do forward list, like a blob list decoding, a reverse list decoding, and try to do that same analysis. You again do a grid argument, and that thing still goes through. And it really is quite similar. You can also, and this was a question someone asked earlier, that Krishnamurti asked earlier, well, there's no penalty because of something like that, but you can actually get information theoretic secrecy as well on top of this. So you can say that, well, James is getting to see a noisy version, and he's trying to also jam. So you want to now simultaneously ensure information theoretic secrecy against James and adversarial and reliability against adversarial jamming for Bob, and then you can get this rate with this additional condition that we don't believe to be necessary, right? So that's nice. It nicely composes with known results, right? Okay. So this bit flip thing I've already talked about. Sufficiently myopic erasure channel I've already talked about. I've already talked about this. Okay, yeah. So let's talk about the insufficiently myopic regime, right? Where things are more interesting. So now let's look at the erasure model here and the erasure model here. And now we're looking explicitly at the insufficiently myopic thing, okay? So now if you think about it, off the top of our head, it seems like nothing should be possible, right? Because there are fewer random erasures to James then he can impose on the main channel. So at the very least, he could just behave like, if there are q fraction of erasures to him, he could just put q fraction of erasures here. So if Bob can hope to decode, so can James, right? So it looks like this should be the same as the omniscient adversary, right? However, note that Bob only wants to decode the message, whereas for James's attack to be successful, he may need to decode the code word as well, right? Because his whole thing is to look at the transmitted code word, try to push towards another code word, and so on. So can we somehow leverage this distinction, potential distinction between messages and code words in the insufficiently myopic regime? And indeed, it turns out that at least for some parameter regimes, this is possible, okay, which we find fascinating. Again, we have nothing like a tight capacity characterization, but we do have something that slightly at least beats the GV bound, the Gilbert-Wassermann bound. Okay? And again, it comes down to the distinction between the message and the code word, the fact that there are many potential code words for each message. Okay? So something like a superposition technique over here is helpful. So let me go into that a little bit. Again, just at a high level. Again, it's the last hour. You guys are superheroes for sticking with me so far. So let me just, yeah, we're all superheroes now, right? So, so firstly, even the converse over here, let's just think about a converse for this. By the way, this is also unpublished and so on, so, you know. So what can the adversary do? So the adversary observes NQ erasures, and whatever is erased to him, he erases. Okay? Remember, Q is less than P, so there are fewer random erasures to him than he can erase. So he can always erase whatever he doesn't see, right? And whatever he does see, so now there's a shorter effective block length. It's of length n times 1 minus q, and the number of remaining erasures he has is n times p minus q, right? So now we can use this mysterious magical LP bound, which is a bound on the omniscient adversary. So now in this remaining n prime length code word, he's really omniscient. He knows everything, and he can force a rate of no larger than whatever the LP bound would imply on this punctured code, right? And so this is an outer bound. It's strictly less than 1 minus p, but it is larger than the standard LP bound. So it's somewhere in the middle. Okay. Now that's a converse, but the achievability that we get is maybe more interesting, and it is indeed strictly larger than the GV bound, at least for some parameter regimes. Now there's a lot to absorb over here. Instead of trying to absorb this, let me just leave it up here while I try to give you a pictorial version of what's happening. And it's a little bit related to that that superposition code that I talked about. I may have to use the superposition code over here by using a different color on top of this color, so that you can hopefully see what's going on. Okay, so let's see what we can do over here. Aha, it looks like I have a rescuer. So sorry, thank you. Okay, so let me talk a little bit while a better job is being done cleaning than I could do physically. So so over here we're going to have we must use stochastic codes, right? James must introduce some additional randomness in his encoding. I'm sorry? Oh, Alice must introduce additional randomness. Good. So it will be sort of a two-layer encoding. Okay. So Alice will first choose just a random code of rate some 2 to the nr. This r will be slightly larger than what may be supportable by a GV code. Okay, just a little bit larger. I'm not even going to worry about how much larger and so on. No numerical calculations here, but slightly larger. So Alice first of all chooses some 2 to the nr clean code words each of length n, right? So these are the clean code words. On top of this, now in the codebook design, there'll also be a masks of size. So basically think of a two-stage encoding process, and in particular as part of the design of the code, you'll also design masks, which are also binary vectors of length n and 2 to the nr of these. So for every message, there's a potential mask. For this message, there's a mask here, and so on. Okay? It's a one-to-one mapping. It's part of code design. Everyone knows all of these. So the people know the code words. They know the masks. Okay? And this, yeah. So what's the point of these masks? These masks will be used to generate that superposition code word, the code word corresponding to the message, and so on. How? So So first of all, Alice chooses, let's say, this message over here, right? And then she chooses this mask. And then using this mask, she'll generate some very low weight noise. Okay? So this mask, it's a random mask that will have like roughly half zeros and half ones. So zeros here and ones here. So wherever there are ones in this mask, she'll flip a bit with probability 1 over square root of n. So she'll use something like a Bernoulli 1 over square root of n noise within the support of this mask, but she won't flip bits in the zeros of this mask. Okay? So what does this do? It ensures that on top of the clean code word that Alice will be transmitting, she'll be transmitting this clean code word, she'll also transmit some noise, deliberately introduced noise, overlaid on top of that clean code word. Okay? Now this noise is independent in the sense that the probability of a bit flip in this location is independent of the probability of the bit flip in this location. There is no bit flips in the zeros of this, but there are bit flips in these locations, right? So the point of this is the following. When James sees his z, so when he gets to see the sum of this vector and this vector, so he sees something like this, he can very likely decode the message. He can decode what this thing is. But there will be, because there will be some random erasures towards him, he'll find there will be some bit flips in this subset that he doesn't get to see because they're erased to him. Now, because they're erased to him, he can't predict where they are. And if he does not erase every single bit that's erased to him, then some of those bit flips will get through to Alice, right? And those bit flips will then act like a signature that Bob can use to try to disambiguate between the list sides. Okay. So let me sort of say it again. So the encoding process is hopefully a little bit clear, right? There's a message and there's a mask. Generate a little bit of noise according to the mask. Add that to the code word, transmit. Okay. James does whatever he does. Bob list decodes, gets a small list size, and then tries to use the signature in the noise to try to say, oh, is it this? Is it this? Is it this? So he tries to guess the likeliest transmitted code word. Okay. Now, if James does not erase every single bit or almost every single bit that's erased to him, then you can argue with a bit of effort that at least some fraction of the bits that Alice has deliberately flipped using the mask get through from Alice to Bob. Okay? And then you can argue that since the mask for one message can't have too high an overlap with the mask for another message, these signatures are not very confusable. Okay? Require some effort, it's doable. Okay? So you can argue that these signatures are sufficiently different. So what this forces James to do is he really has to erase basically almost everything that's or a large fraction of what is erased to him. So since he has to do this, this weakens his achievability, and you can get something at least slightly larger than the GV bound. Okay? Very unsatisfying because it's the big picture approach. This is all I have. The actual calculations are a little bit messy. I'm not going to try to attempt that even. Okay? But that's what we have. Okay, so this begins to show why, in the insufficiently myopic regime, you really do need a combination of ideas from information theory, like randomness, but also coding theory, like these things like the Plotkin bound for the converse, from an achievability perspective, list decoding, all of that jazz, right? So there's really an interesting interplay of ideas happening over here, which I find fascinating. Okay. All right. The last thing I want to say for the myopic thing, and then I'll try to do a very quick, similar 15-minute high-level overview for the online adversaries, because I promised that will be whatever. But first, I want to spend maybe 5 to 10 minutes just talking about myopic quadratic adversaries, because really maybe this is maybe the most natural myopic channel that one can hope for. So again, it's a myopic adversary. Alice transmits something to Bob. James has a AWGN channel, and then you can add some quadratically constrained noise. Notice I've explicitly allowed for a key over here, not because I'm fundamentally interested in the key region, like what happens when you have common randomness, but it helps to actually begin to see what happens if you allow a key, then a smaller key, and then no key. Okay? So in terms of explaining what's happening, let's make our life easier by first allowing ourselves to have a key, potentially even a large key. then keep shrinking that key size, and that process of reducing the key size will start exposing more and more intricate behavior. Okay. All right. So yeah, the differences, there are some differences. You have to replace the ring by strips. Things are continuous, blah blah blah. So there are many different things. But okay, so let's just pictorially see what's happening. So suppose, and this was known due to Anand Sarvate and others. There's actually a slight mistake in his proof. He didn't have quite this region. There were some differences, but you know, the mistake is minor, I think, and easily correctable. Really, due to him, he had this result. If you allow an infinite amount of common randomness between Alice and Bob, then there are really three sorts of behaviors. Okay, in a certain part of the parameter regime. So what is this parameter regime? This x-axis is the NSR, noise to signal ratio, the ratio of the noise that James can impose to Alice divided by Alice's code words. So this is the NSR of the main channel. Again, think of it like P. Okay, so this is like P. This is like the noise that James can put on the main channel. Think of this like Q. Think of this like the NSR towards James. Okay, so this is a two-parameter space over here. Okay, so as this increases, James becomes more and more powerful. As this increases, there's more and more noise towards James. Okay, that's one way of thinking about it. Okay, so if the NSR is in this region, you can prove nothing is possible. Regardless of the amount of common randomness, the capacity is 0. Okay, so that's this gray region over here. If you're over here in this red region, you can prove that the capacity is the list decoding capacity of this quadratically constrained channel. And if you remember what we said in the second or third R, that's half log P over n, not half log 1 plus P over n. Okay, so that's half log P over n. That's somewhere over here. And in this middle region, there's more intricate behavior. There's a different expression. This is what we call the myopic list decoding rate. Okay, and you can prove again that the capacity over here is this other expression, the myopic list decoding rate, rather than the list decoding rate. Okay, all right. So that's with unbounded amount of common randomness. Okay, and you really do need an unbounded amount of common randomness to get exactly this result. Now, what happens, and we can show this with our techniques, is, so suppose you have a fixed amount of common randomness. In this case, yeah, there should be 0.2 n. So let's say that the key rate is 0.2, or n times r key is 0.2 times n. There's a missing n over here. Okay. So the 0 part is still 0. We have a tight capacity characterization over here. This is the blue region. This is the red region. Again, we have a tight capacity characterization. In between, we don't quite know what's happening. We have an inner bound, we have an outer bound, but the dotted region, our inner and outer bounds don't match. Okay, and and you can take a cross section over here. You can take this line over here, and given this line, here our regions don't match. Here we have a tight capacity characterization. It corresponds basically to this red, you know, the list decoding half log P over n curve over here. Okay, all right. And I'll talk about our techniques later, so in particular about myopic list decoding and so on later, but first I just want to show you what the results look like. Okay? As the common randomness increases, then you start converging towards that infinite amount of common randomness. So now if you have n bits of common randomness, again there should be an n over here, then we don't know what's happening only in the small region, but everywhere else it starts looking more like that unbounded amount of common randomness. And if you have, now this is quite interesting, if you have only log n bits of common randomness, if the amounts of common randomness you need is just log n, even then you can say quite a lot about a fairly large parameter space. Okay, so really I would say that there are really two uses of common randomness. Okay, one use of common randomness is so that the code book can be sufficiently expanded, so that there are sufficiently many code words so that you can confuse James. So remember, in our first step of our proof, we would like there to be many different code words, at least 2 to the epsilon n code words in James's oracle given set. So if you have common randomness, you could imagine taking a much larger code book, and then Alice and Bob using that code book to shrink their actual code book size, but from James's perspective it's still a large size, right? So common randomness can be used to artificially inflate James's confusion, right? So for this you need a linear amount of common randomness. But if you already have James being confused, which you do in this fundamental blue region, then you don't need that, or in this red region, you don't need that linear amount of common randomness. Just a logarithmic amount of common randomness suffices to do that second step of disambiguation. So once you have list decodability, remember you have a constant size list, and then just log n bits of common randomness allow you to disambiguate down to a constant size, down to unit size, right? So this is what I meant by starting off with a large amount of common randomness, keep reducing it until you start seeing interesting behavior, right? So firstly, just this is surprising to us, the fact that there are two different, I mean, at least from an achievability perspective, there are two fundamental uses of common randomness. One is to confuse James, but then the other is to disambiguate from a list decoding perspective. Okay? And the scaling for these two behaviors is quite different: linear in n and logarithmic in n. Okay. And then what if there's no common randomness? So then I believe our techniques are weak, but I think, for example, we can extend this blue region more and so on. But this dotted region, we don't know what's happening in here again. Here we have an achievability and a converse, and this, broadly speaking, follows the same proof technique as before with one new idea, that of myopic list decoding, which I'll talk about briefly, again at a very high level. In the converse, something interesting is happening. So there's sort of two different converses, which for a zero region, something like this and something like this. And this part is also quite interesting. It pertains to something called this Plotkin push attack, so there are two different symmetrization attacks, which I'll talk about briefly. One is more natural, that people will have seen before. One is slightly less natural, and I'll talk about both. Okay. So okay, so this is what happens with no common randomness. This is really what we're most interested in. And again, just to unify all of that, this is just a unification of the previous figures. Okay, and these are what the capacity curves look like, and so on. So first of all, capacity, the proof for the converse. The proof for the converse, broadly speaking, actually follows what I already mentioned briefly, a couple of hours ago, which is James uses his power in two different ways. One to scale down Alice's transmission, and then the other to add some random noise. Okay, and both of these, so the effective channel then becomes like a different AWGN, and then you can do an optimization, and when you do that optimization, it turns out that in this region, there's a certain capacity. In this region, there's a different capacity, and that just happens because the switch in behavior just happens because when you do this optimization, at some points that optimization happens inside of a set, a convex set. The other boundary, it happens just at the boundary. So that's why you have different scaling behavior. Okay, but the other types of converse attacks. So these types of converse attacks, remember, they take the channel and they convert it into a distinct discrete memoryless channel, and therefore this works regardless of the amount of common randomness you have, right? Because the capacity of a discrete memoryless channel is independent of the amount of common randomness shared between Alice and Bob. Like you can take the Fano's inequality and make it work even with common randomness. All the other steps in the usual information theoretic converses go through even with common randomness. So common randomness does not change the capacity of a discrete memoryless channel. So these are very robust. But if you do not have common randomness, then coding theoretic techniques come into play. So let's talk about what sort of coding theoretic techniques may be useful. So one is a Z agnostic attack. So this attack is sort of the first thing you may think of when you're thinking about what James may do to confuse Bob. Okay, what he does is just chooses a random other code word, adds it to the transmission, and now Bob has two different things. He doesn't know which was transmitted, right? And clearly, if the NSR of James is larger than 1, that is to say, he has at least as much power at his disposal as Alice does, then he can always choose another code word, right, and add that to the transmission. So that's why you have a vertical line over here. As long as James has at least as much power or more power at his disposal than Alice does, he can just add another code word. Bob gets a sum of two different code words, can't distinguish between these two. There's no common randomness, there's nothing else to distinguish them, right? So that's a problem. That's why we call it a Z agnostic attack. It doesn't depend. James can do this even if he doesn't see anything, even if his NSR is infinity, right? He can just add this. A different attack he can do is the following. Okay, so this is a Z aware attack. What he does is this is more coding theoretic. It's more related to the Plotkin bound, which if you look in the proof technique and dig into it, it really begins to resemble the Plotkin bound attack. So what he does is, he looks at the Z he's getting, chooses a random code word, some x prime, that he knows that Alice could potentially use, and then tries to push between these two. Okay? So by which I mean, he's just going to take coordinate by coordinate. He sees some Zi, so there's some Z vector that he's seeing, some Z vector in Rn. So he sees some Zi, and he's chosen some x prime vector, some other vector, some random vector. He looks at this x prime I, and the Si he adds is equal to x prime I minus Zi by 2. Okay, so he just adds something so that what Bob would get. So what would Bob get? Bob would get this plus xi, and then when you calculate this out, it will basically be equal to x prime I by 2 plus xi by 2 minus some additional noise, some sz I by 2. So basically something like that. So it basically symmetrizes between two different code words and something else. Okay. Now, okay, without going into the details, basically this does depend on the type of codebook structure and on his observations. And when you do the math and do something related to the Plotkin bound, you can argue that in this part of the parameter space, with constant probability, his attack is going to work, and therefore it's a converse attack over here. Okay. So again, an interesting interplay between achievabilities and converses, worth highlighting. And techniques for achievability is related to this myopic list decoding. This is the last thing I want to highlight in this myopic adversary business. So so let's just see what's let's just see what's useful over here. So yeah. So James is seeing a particular Z over here. The code words are distributed in some strip over here. The truly transmitted code word is maybe this, but all of these are sort of roughly equally likely. So there's some quasi-uniformity happening, which you have to worry about the technicalities due to the fact that the probability distributions aren't quite uniform, but it can be handled. Okay, but one quite useful further relaxation of the notion of list decoding, which is quite useful in this context, is the following. So it turns out that okay, in this strip, James, if he knew that this was exactly the code word being transmitted, then there's a specific push attack that he could use to force the list decoding rate to be quite small. But actually, he has some uncertainty within this strip over here, right? So by myopic list decoding, our relaxation is the following. Instead of demanding that for every potential received vector y, there be no more than a constant number of code words within your possible thing, you average this quantity over James's uncertainty. Okay? So what do I mean by that? James can use any S vector he wishes, but once he fixes his S vector, you have to average over the potential code words that Alice could have transmitted over the strip. Okay? And as long as for most of those code words, the corresponding balls don't have more than a small number of code words within them, then you'll say that this is myopically list decodable. Okay? And this is good enough, right, for most purposes, because James is really uncertain about which of these 2 to the epsilon code words is transmitted. And as long as for most of them your thing is going to behave well, then that's good enough. And this is really what allows us to get a much larger rate region, right? That's myopic list decoding. The techniques to do with this are, different types of random variable decompositions and so on. And I invite you to look at our full paper. We just submitted to ISIT. All right, so that's this. Now we have 20 minutes, and okay. So I'm going to leave it open to the audience or Vinod or so on. What my plan was to talk about one more model, but that's always a temptation, right? I'm happy to not, okay? I am happy to, I really am. But if people are saturated, or if maybe Vinod is the best judge, we can also convert that to discussion time, or just happy chill time, or whatever else people would like to do. Okay? So I don't know. What do you think, Vinod? Okay. Okay, so very big picture, right? So let's go for the big picture there. Okay. All right. Okay, and again the wrong slides. So okay. So what's a causal adversary? So a causal adversary is another one where the adversary is truly adversarial. He gets to see X noiselessly, but causally in an online manner. That is to say, for example, like maybe he can erase at most p times n bits, but to decide whether to erase a given bit or not, he can only base his decisions based on what he's seen so far. Okay? So the natural indexing according to time and so on. Now, notice it's a little bit like a budget allocation problem, a real-time budget allocation problem. You know you have a total budget. You don't know whether to use your budget right now in the beginning or to use it later, right? So you can view it in that manner. Now, these channels, we've begun to understand what their behavior is like. In fact, we have capacity characterizations for the erasure version, for the bit flip version, for the query symbol version. Recently, a a characterization for the quadratically constrained version. So we have these things. Venkat has some non-trivial results for the deletion channel. So we're beginning to understand how these things behave. So let's begin with the capacity for the binary erasure channel. We know this capacity to be 1 minus 2p basically. So as long as p is less than a half, it's 1 minus 2p. If p is greater than a half, nothing is possible. Okay. Now these results are firstly surprisingly subtle in a variety of different ways. So let me just tell you first of all what the results are, then maybe a little bit about the techniques and so on. Okay. So firstly, actually maybe there's already a slide in a different talk to do with what the results are like. This is a talk that Anand gave at ISIT. So maybe let's just talk about that. Yeah, and a generalization of this would be, if instead of being exactly causal, if the adversary, who now mysteriously is called Calvin, so at some point we realized, we used to be Alice, Bob, and Calvin, A, B, and C. Then we realized, Jammer, James, it has to be James, right? So it's an evolutionary process. But anyway, so Calvin has to decide how to jam or not, depending on not just the current symbol, but some possibly delayed version of this thing. Okay, and this delta could be negative. It could be a delayed version. It could be positive. It could be a look ahead version, right? So this is just a framework to sort of describe different types of adversaries. So in this case, the types of results are the following. So if you think about it, if the adversary is completely oblivious, he doesn't see anything as to what is being transmitted. This is the fully oblivious adversary. It turns out, we didn't prove it, but you can prove that in this case the capacity is actually 1 minus p. It's the same as the capacity of the binary erasure channel. Okay. If you have if you want an erasure capacity, so that's what I just said using the previous slides. So then the capacity is 1 minus 2p. Okay. But interesting things happen with other types of delays. So even if you give yourself epsilon n look ahead, actually significant look ahead, not just the current bit, but epsilon n bits ahead, the capacity is still basically 1 minus 2p. Okay? So knowledge of the future doesn't really impact the capacity too much. But with full look ahead, it is substantially worse. With full look ahead, I mean, basically, if the adversary knows everything, then we know it lies somewhere between the GV bound and the LP bound, right? But with even a single bit of delay, it turns out that, oh, right, so this is not yet the full thing. So this is full of growing delay. Now, yeah, the slide is mislabeled, so forget what's written on the slide, unfortunately. But with even a single bit of delay, the capacity comes back to being 1 minus p. But you have to allow stochastic encoding. If you have a single bit of delay, but you demand deterministic encoding, then the capacity is still 1 minus 2p. Okay? So let me repeat. The capacity is, the baseline capacity is 1 minus p. If you're causally restricted, exactly causally restricted, it's 1 minus 2p. If you delay yourself by even a single bit, then and allow stochastic encoding, it snaps back to being 1 minus p. Okay, but you have to allow stochastic encoding. If you demand deterministic encoding, it becomes 1 minus 2p again. Okay, so that's the punchline of this paper. Now, maybe instead of talking about the causal paper, the exactly causal paper, which is doable, let me instead give the high level ideas for the achievability in this paper, this 1 bit of delay paper, because somehow in some sense this is maybe in my mind a little bit easier to explain, and it also has some interesting ideas which hint at the ideas in the exactly causal paper. Okay, so let me focus on this in the remaining 5 to 10 minutes, which and then I'll be happy to try to answer other things. So basically, it's related to what I wrote on the board over here, which is, having a clean code word, having a mask, a fingerprint, and something, and then trying to decode. Okay, which it also behaves in something like a similar manner. So what does Alice do? so Alice is going to try to transmit at a rate 1 minus p minus epsilon, but she'll add a noise fingerprint to this clean code word, to the base code word. And then Bob list decodes, and then he tries to disambiguate based on the signature of the noise. Okay. Now that's just a very high level, but what does it mean to add noise? What does it mean to oh, right. So that's a converse which we won't worry about for now. So let's look at a more concrete code design. So so let's say you have a code word like this. This is a clean code word. This is the code word that Alice would have transmitted based for her particular message. And she also has a mask, but now these masks have, instead of just being zeros or ones, they have differing probabilities. So over here, the probability of a bit flip is q1, here it's q2, here it's q3, and so on. So every location has a different probability. Okay? So each code word has a corresponding mask. There are 2 to the nr code words, 2 to the n times 1 minus p minus epsilon code word, and 2 to the n times 1 minus p minus epsilon masks. Okay, one mask for every code word, each with a randomly chosen mask like this. Okay, so how is the code word actually generated? How is the actually transmitted code word generated? Choose a clean code word, use the mask to generate some very low weight noise. Okay, and then XOR these together, transmit that. Okay, now notice that James, when he sees or Calvin or whatever, the adversary, when he sees the transmitted code word, again, he doesn't know what the current bit is, right? And each bit, the noise in that bit is generated in an IID manner, right? So it's hard for him to predict, is there noise in this bit or not, right? So what you can show is that if you're transmitting at this rate with this scheme, firstly, there'll be, each of these masks looks very different just from this labeling perspective, right? There'll be sort of k different levels, and because there's a code word of length n, there are k levels. It's basically like a k-ary code word over length n. So these code words are sort of very distinct looking, right? These noise level code words are very distinct looking, and therefore the corresponding noise levels in these corresponding signatures are also quite different. Okay, so if James does not erase basically everything, so basically everything that James does not erase contains a very clear signature of noise levels. So when Bob list decodes, he list decodes down to a constant list size, and then he looks at the particular locations which have not been erased. In these locations, he knows if this was the message, this is the code word corresponding to that, and this is the mask corresponding to that. Now let me look at my list decoded message and see if the number of bit flips in the Q1 locations is approximately Q1 times the number of locations, if the number of bit flips in the Q2 locations is approximately Q2 times the number of Q2 locations, and so on. Okay. So that's how I judge the quality of my signature. If the signature looks good, then I say, okay, this is the truly transmitted message. Okay. That's the decoding procedure. Now, and there's some counting arguments which I'm not going to go into, but these counting arguments basically come down to saying, well, James, you know, it's like James has a bed sheet, but this bed sheet is too small to fit into the whole bed. I mean, I'm saying this because I'm the guy in the household in charge of changing the bed sheets. I hate it because it never fits, right? You try to do something here, something else goes out of the whatever. So the same thing happens with this thing. James tries to erase these bits, but then these bits leak some signature. He tries to erase these bits, but then list decoding is too weak, and so on. So you do some counting arguments, and basically it comes down to the fact that essentially James cannot hide the signature. It really just comes down to that. Okay, that's the achievability idea. Okay, so that's what happens with a single bit of delay. If there's no delay, then none of this works. Then you're down to a 1 minus 2p type converse. And the last idea I want to finish with, the last big picture, I will not attempt to give the achievability for this 1 minus 2p, but the last achievability I want to focus on is to do with this the last converse I want to focus on is this 1 minus 2p thing. So what does James do? In this causal case, he waits until something like 1 minus 2p bits have gone by. He does nothing at all. Okay, and then in the remaining 2p times n number of locations, he's going to do the following. So in the remaining 2p times n number of locations, since he can erase pn locations, it's as if he can erase close to half the locations in the remaining code word, right? But this half should remind you of something. It should remind you of the Plotkin bound that we had earlier, right? So that's where this 1 minus 2p comes from. So even if he doesn't do anything in the prefix, if you're trying to transmit at a rate above 1 minus 2p, Bob must have some confusability in this prefix. Okay? Then given Bob's confusability at this point, because you're transmitting at rate larger than 1 minus 2p, Bob is confused. James is maybe potentially similarly confused, but nonetheless, there's some confusion existing in this situation. The residual code word length is 2pn. James can erase half. So it's just like a punctured code over here. And James chooses some random x prime, tries to push it towards that, and using a version of the Plotkin bound, you have to do it carefully because it has to work even against stochastic encoding. It's non-trivial. It does require some effort to make sure it works against stochastic encoding as well. You can get it to work. Okay, that's what you do with the erasure attack. It turns out that there's a similar attack for the bit flip thing, except instead of just waiting in the prefix, what James should do in the prefix is add a little bit of noise. And why should he add a little bit of noise? It's just like that curve I drew for the Burle-Camp capacity in the beginning, right? So there's sort of two stages. In the first stage, even adding a little bit of noise, because the entropy function has such a steep curve that dramatically reduces the capacity, and then from that point onwards, in the suffix, you can then do sort of a more mindful attack based on the specific code book. Okay, and then there's some optimization problem to be solved based on what he can do. So again, he adds some noise in the beginning to make sure that Bob, no matter what he does, his list decoding bound is still somewhat large, and then at this point, then he has enough bit flips to be able to make sure that the Plotkin bound works in the suffix over here. Okay. What's truly remarkable for this problem is that, in fact, not only is this a converse, but for some magical reason, there's also a matching achievability. It's not based on this specific attack. Regardless of James's attack, you can actually match this capacity, okay, and that requires entirely new ideas and so on, which I will not get into. I mean, it's 5 minutes till 4:30, and I will not get into it. Okay. I'm done. So, thank you.
No, no. So, all right. So, thanks, Sidharth. We had a really wonderful slide. So, like the superhero is.
Fine.
All right. So tomorrow, for those who are staying in, the mind is breakfast at 8 and the bus will leave at 8:30. So please be on time. And we'll all meet at IIT tomorrow. We'll start there.
Okay. Thank you again for your patience. I really appreciate your efforts.